Welcome to the deep dive. Today we're looking way beyond just the next EV battery. We're diving into what looks like a genuine technological revolution, one that might just kill range anxiety for good.
Yeah.
Our mission here is to really unpack the sources covering these, well, frankly, revolutionary EV battery technologies,
Yeah.
the kind that change how cars are even designed.
Yeah.
And crucially, dissect that very deliberate strategy driving China's dominance in this whole area.
And this is one of those topics where you see the numbers and it's an immediate aha moment,
Definitely.
especially if you follow EVs at all.
Definitely.
Our sources are pointing to two, well, almost unbelievable advancements coming down the pipe. First up, there's this potential for a new kind of solid-state battery. We're talking a 1,000-kilometer range.
Which is already amazing range,
Mhm.
but here's the kicker, the bit that really changes things.
Yeah.
The sources suggest that battery pack could weigh only about 100 kilograms.
Exactly. And just to give you some perspective on that, right? Your typical battery pack today, in a sort of mid-sized EV, it's often 350, maybe up to 500 kilos, vary. So cutting that down to 100 kilos, that fundamentally changes the car's dynamics, its efficiency, how it handles, its entire safety setup even. It's like a total design revolution.
Okay, so 1,000 kilometers from 100 kilos.
Yeah.
Wild. But then there's another innovation, this one U.S.-based promising, get this, a potential maximum range of up to 1,600 kilometers on one charge.
Yeah, 1,600.
That's not just about charging faster. That's potentially eliminating the need to charge on like an average road trip altogether.
It really is a leap, isn't it? Not just a small step. So I guess what we need to figure out today is, well, how are these numbers even possible?
Right.
We're going to try and define the two big forces shaping this. First, we'll unpack the pure tech breakthroughs, the battery architectures coming from China and the US, focusing on that huge jump in range, the weight reduction, and maybe the cost.
Oh.
Then we'll pivot. We need to dissect that second force, which might actually be more powerful in the long run. China's deliberate strategic model for industrializing these techs at massive scale and basically leading the whole global industry.
All right, let's kick off with the tech in section 1. This race for range is incredible. Let's start with the Chinese side. Their focus seems to be on solid state, making batteries lighter, more durable, really solving problems at the component level.
Yeah, the target is that 1,000-kilometer range from a 100-kilo pack. And to get there, you have to tackle issues that current liquid lithium-ion tech can sort of work around.
Okay.
And the Chinese researchers seem to be hitting these problems with, several micro-innovations all at once.
And some of these sound like pure chemistry magic. I mean, the sources mention things like iodine glue. What on earth is iodine doing in a battery?
Right. It sounds weird, but it tackles a really critical problem in solid-state batteries. Contact impedance. Basically, when you swap out the liquid electrolyte for a solid one, you get, less than perfect contact between that solid electrolyte and the anode.
Okay, like tiny gaps.
Exactly. And that poor contact, it slows down the lithium ions, limits power, and can eventually lead to things like dendrites, nasty little spikes inside that cause short circuits or kill the battery early.
So the iodine acts like a filler, a mediator.
Precisely. Yeah. The researchers add iodine ions, and they act as this sort of glue, filling in those microscopic gaps and voids that pop up during manufacturing or just from charging and discharging. By making the contact better, they smooth the path for the lithium ions. More energy stored, delivered more efficiently.
Huh. That's pretty clever chemistry. But hang on. Batteries physically expand and contract, right? Every charge cycle.
Yeah.
How does a solid structure handle that stress? Wouldn't it just crack?
Good question. That's where the flexible electrolyte comes in. This was developed by the Chinese Academy of Sciences. Your standard solid electrolytes are pretty rigid, yeah. And that expansion and contraction would fracture them over time. But this new material is a solid polymer electrolyte. It can actually flex, bend a bit, accommodate those volume changes during charging and discharging without breaking apart. That's absolutely vital for making these things last in the real world, in an actual car battery.
Makes sense. And then for safety, always the big worry with packing more energy in is there's this durable fluorine shield.
Yeah, this one's from Tsinghua University. It's basically a fluorine-based coating applied to the electrolyte. Fluorine compounds are known for being super stable.
Right, like Teflon.
Kind of, yeah.
No.
So this shield makes the battery much more resistant to physical knocks, impacts, and crucially, fire. But, and this is the clever bit, without blocking the ions from moving, it doesn't kill the battery's performance.
Okay, so you've got better contact with the iodine glue, better flexibility, better safety with the fluorine. If you put these microfixes together, do they actually add up to big performance gains? Are we seeing that in the numbers?
We are, yeah. The sources point to AVC lithium battery. They're all solid-state silicon battery chemistry. It's achieved an energy density of 430 watt-hours per kilogram.
And how does that compare?
Well, right now, the sort of high end for mass market performance batteries is maybe nudging 400 kilograms if you're lucky. Hitting 430 isn't just a little step, it's a pretty significant jump in energy density.
Okay.
It means packing more power into less space, less weight. That's absolutely critical for hitting that 100-kilogram target we talked about.
All right, now this is where it gets really interesting, I think, because the U.S. approach sounds completely different. It's not about tweaking the chemistry in the same way. Let's shift focus to the U.S. side, this idea of a cell-less revolution. It's pioneered by 24M, spun out of MIT, and the core idea is kind of mind-bendingly simple. Just get rid of the individual battery cell.
Yeah, it's a total architectural rethink. The concept's called Etop, which stands for electrode to pack.
Electrode to pack.
Think about, say, your laptop battery or a normal EV pack. It's basically hundreds, sometimes thousands, of individual little cells, right? Each wrapped up in its own casing with terminals, support structures.
Yeah, lots of packaging.
Exactly. Etop just bypasses all of that. It says, let's get rid of the individual cell as a component.
So, how does it work then? If you don't have cells, what do you have?
Well, they process the anode and cathode material into these thick, sealed electrodes, and then they stack these electrodes directly inside the main large battery container. They're basically cutting out all the inactive material.
What I felt is inactive material.
All the metal casings for each little cell, the rigid bits holding them in place, the safety gaps between them, even some of the internal cooling stuff needed when you have lots of separate cells heating up.
So you're basically just carrying the active battery chemistry, not all the overhead, the packaging. What does that actually mean in performance terms? What's the gain?
It's staggering, according to the sources. They suggest packaging efficiency improves by up to 80%. 80, because you're using all that volume for actual energy storage, not structure.
Wow.
And that translates directly into a potential range increase of up to 50%, which is how they get to that potential 1,600-kilometer maximum range figure.
That just sounds like pure disruption. But
Yeah.
what about the risks? I mean, if you take out all that structure, all that inactive material, isn't that potentially risky? Safety, heat management.
That is absolutely the critical engineering challenge, yeah. It's the risk you take with such a radical design. But the Etop design tries to counter this by simplifying the assembly.
How so?
Because it's so streamlined, no fiddly individual cells, they project that production costs could fall by up to 40% once they scale up to, gigawatt-hour levels.
40% lower cost. That's huge.
And crucially, that simpler process means potentially a single highly automated machine could handle the whole production and assembly line, which makes it, well, ideal for bringing manufacturing back onshore and for qualifying for things like the U.S. Inflation Reduction Act tax credits. So it feels like a design engineered for both massive performance and the current geopolitical situation.
The contrast really is stark, isn't it?
Yeah.
One side focusing on perfecting the chemistry, durability, micro-innovations, the other going for this macro-architectural efficiency leap.
Yeah.
But like you said earlier, just having the tech doesn't guarantee market control, which leads us perfectly into Section 2. Let's try and decode China's strategic dominance.
Right. And what's really fascinating when you dig into the sources here is realizing China's lead isn't just, oh, they have the mines. It's way more about a highly coordinated, very strategic, long-term industrial plan. I mean, just look at the numbers that define who controls the market right now. China produces something like 80% of the world's battery cells.
80%.
80. And 85% of cathode materials, over 90% of anodes. They basically own the industrial platform that everyone else currently relies on.
And the sources show they're not just making one big risky bet on a single perfect battery tech, which you see a lot in competitive R&D. They're using this multi-lane platform-based strategy. What does that mean exactly?
Precisely. Western companies often seem to chase that one holy grail, maybe the perfect all-solid-state lithium metal battery, right?
Yeah.
China, though, seems to be pushing multiple different chemistries forward at the same time. Their whole industrial base is built to be flexible, it can pivot, and it's structured to use the manufacturing lines they already have to scale up new, viable technologies almost immediately.
So what are these different lanes they're pursuing?
So lane 1. Keep making lithium-ion. Obvious, right? Keep the cash cow going. Lane 2, aggressively scale up sodium-ion.
Sodium-ion, why is that so important?
Two big reasons. One, sodium is everywhere. Dirt cheap, abundant. Minimal geopolitical risk compared to lithium, which is concentrated in fewer places. Two, and this is critical, making sodium-ion batteries largely reuses the existing lithium-ion manufacturing equipment and processes.
Wow. So they don't have to spend billions retooling everything.
Pretty much. It slashes the cost and time to scale up. Then, lane 3 is the pragmatic one, industrialized semi-solid batteries. This is what we might call the bridge to solid approach.
Like CATL's condensed cell that made headlines.
Exactly like that. They scale up that intermediate step now. It generates revenue, they learn how to manufacture at scale, build expertise, all while the full solid-state tech is still maturing in the labs.
That explains that staggering statistic you mentioned. 99% of the world's commissioned solid-state cell manufacturing capacity right now is in China. They're building the factories before anyone else.
And that kind of aggressive scaling, it's only really possible because of Pillar 2, policy, subsidies, and market certainty. The government provides massive, sustained support, like that multi-year neighborhood electric vehicle NEV purchase tax relief.
Let's pause on that NEV relief. Those numbers are huge, right?
They are enormous. That tax relief was extended through 2027. It totals around 520 billion Chinese yuan.
Which is
Roughly 70 billion US dollars. 70 billion. That kind of long-term commitment just removes market risk for investors and manufacturers. The government is essentially guaranteeing stable, high demand for years.
So companies feel safe making those huge upfront investments in factories.
Exactly. It signals certainty.
Yep.
And they apply that same playbook consistently. Look at sodium ion again. They didn't just wait for it to become commercially competitive on its own. They basically forced the market.
Oh.
They create demand proactively, government tenders for big projects, but with clear financial incentives baked in. For example, setting price caps, the sources mention, around $150 per kilowatt hour for energy storage systems using sodium ion.
Okay.
That made those early projects bankable, viable from day one. It yanked the technology straight out of the lab and into real-world deployment fast.
This really sounds like a system where creating the market and regulating it are totally intertwined. Which brings us neatly to Pillar 3, patents and standards. This idea of publish the standard, then buy to the standard.
Oh, this is a masterstroke of shaping the market. Seriously, take sodium ion again. They established the national standard. First, it's got a designation, GBT 44265 2024.
Okay.
So they essentially told the industry, right, here are the performance specs, the safety metrics you must meet. Then they certified suppliers who could actually meet that standard. And then they put out a tender or a major project requiring that standard at that preset capped price.
So they set the rules of the game first.
Exactly. They dictate the terms of technology adoption before the market even fully forms. And you see the result in patent filings, too. CATL has been way out ahead globally in patent growth since around 2018. They're writing the rulebook and winning by it.
And that kind of top-down coordination only works if you have Pillar 4. Midstream control and coordination.
That's their main leverage point, absolutely.
Wow.
Their dominance over those middle steps, refining the raw lithium, nickel, graphite, making the precursor materials, the components, the actual cell production itself. Controlling that whole midstream creates significant cost hurdles and qualification barriers for any global competitor trying to catch up. And they even formalize the coordination. There are institutional groups, like the KSIP Alliance mentioned in the sources.
What does that do?
It pulls everyone together, the cell makers, the car companies, government ministries, research institutes to align their technology roadmaps. They have an explicit goal, build a complete all-solid-state supply chain in China by 2030. It's vertically integrated planning, from the mine to the finished car.
And underpinning all of this seems to be Pillar 5, which feels almost like a cultural or strategic philosophy difference, scale over perfection.
Yeah, it's pragmatism writ large, isn't it? Instead of waiting maybe 10 years for the absolute perfect battery, they focused on scaling good enough tech first, like their earlier push with LFP, lithium iron phosphate batteries.
Which weren't the highest energy density, but were cheaper and safer.
Exactly. That approach got them market leadership, drove down costs incredibly fast just through manufacturing experience, and built that foundational industrial platform we talked about. Now they're applying the exact same logic to semi-solid batteries.
Get them into the market now.
Industrialize them for near-term revenue and learning while also funding the R&D for the full solid-state future. It's like they'd rather have, say, 60% of the market today with a 90% perfect battery than 0% of the market waiting indefinitely for 100% perfection.
Okay, if we connect that whole strategic picture back to the global scene, this kind of industrial scale means even rival automakers outside China pretty much have to engage, right? Which takes us to Section 3, global collaboration and the hurdles ahead. We're definitely seeing a shift in how Europe, for instance, is working with Chinese battery firms.
Yeah, the dynamics moved on. It's not just about buying cells anymore. It's shifting towards joint R&D plus localized production. You see big European automakers, BMW, Audi, are mentioned deepening partnerships with the Chinese giants like CATL, EVE Energy. And often, they're building factories in Europe using Chinese tech and expertise, but serving the local European market.
So the strategic logic for the European car makers is pretty clear then. It's basically a European car tech plus Chinese battery solution model. Is that fair?
That seems to be exactly it. It's an acceleration strategy for them. It massively cuts their own R&D costs and speeds up their whole electrification timeline because they can just plug into China's established manufacturing prowess.
And we're seeing real results from this already.
We are. The sources mentioned BMW road testing an i7 prototype back in May 2025, equipped with a full solid-state battery. So this tech is moving fast, from lab benches into high-end, real-world cars.
And the overall market seems ready for this scaling, right? What do the numbers show for current EV adoption and maybe more importantly, future projections, especially for solid state?
Well, EV adoption is still growing steadily. In the EU, registrations hit just over 1 million cars between Jan and July 2025. That's about 15.6% of the total market. So solid growth.
Okay.
But the projection for solid-state batteries specifically is just enormous. The
Mm.
global market for them is forecast to reach 614.1 gigawatt hours by 2030.
614 GWH. That's huge scale.
Yeah, that puts it well into the trillion yuan market level. Massive potential.
A massive potential, but achieving that kind of growth relies on overcoming some pretty serious practical hurdles that our sources flagged up. Let's quickly touch on those three big challenges to commercialization.
Right. Number one, and probably the most immediate barrier for getting these into mainstream cars, is cost control. Because these advanced chemistries, they often need super specialized, maybe ultra-clean manufacturing environments. The bottom line is, right now, full solid-state batteries are something like 3 to 5 times more expensive to make than traditional lithium-ion.
3 to 5 times, ouch.
Yeah. So unless they can bring that cost down fast, these stay as high-end niche technologies for a while.
Okay, cost is number one. What's number two?
Standardization, or rather, the lack of it. If China and Europe are going to be the two biggest hubs for making and using these things, they really need to agree on how to test them, what safety standards apply.
Right. That seems critical for trade.
Absolutely critical. The sources say significant differences exist right now between Chinese, European, and even U.S. testing methods and safety rules. That's a massive headache for manufacturers.
Yeah.
Imagine trying to sell a car with a new battery type globally if you have to go through completely different expensive safety certifications in every single major market. It slows everything down. Without international agreement here, hitting that 613 GWH global market number by 2030 gets a lot harder.
Okay. Cost, standardization.
Yeah.
And the third hurdle.
Mm-hmm.
It's a long-term one, isn't it? Recycling.
Yep. The end-of-life problem. These unique materials, these complex new structures, whether it's the iodine-doped solid-state packs or those cell-less Etop designs, they're going to need completely new specialized recycling processes.
We can't just chuck them into the existing lithium-ion recycling streams.
Exactly. The infrastructure we have now just wasn't built for them. If we don't figure out how to recycle these new batteries efficiently and safely, we're just swapping one environmental headache for another, potentially more complex one down the road.
So we've covered a lot of ground here. We started with that really clear tension. On one hand, these potentially revolutionary engineering designs like the U.S. Etop architecture aiming for 1,600 kilometers, and on the other, this highly coordinated state-backed strategic scaling machine that China has built using that multi-lane approach. It really feels like a race between pure engineering disruption and sheer platform dominance.
It does, yeah. And if you look at those huge projections, that 614.1 GWH global market by 2030, maybe the real question for you, the listener, to mull over is this. Given the battery is the absolute heart of an EV, and the technology is advancing this fast, how quickly is the EV you might buy today going to feel, well, functionally obsolete? especially when the underlying tech seems to be moving much faster than the international bodies trying to set the safety standards and testing rules can possibly keep up. The tech might be ready, but is the world standardized enough to actually adopt it smoothly and globally?
That's definitely something to think about. Thank you for joining us for this deep dive into the future of the EV battery.